My name is Jessica, and I'm a part of the Business and Marketing subgroup. We're very happy that all of you are here today. And before we start showing you this year's team and our car, I want to thank last year's team and last year's car, Freya, by showing you a little video.
Watching cityscapes turn to dust. Filming helicopters crashing in the ocean from way above. Got the music in your baby, tell me why. Got the music in your baby, tell me why. You've been locked in here forever and you just can't say goodbye. Kisses on the foreheads of the lovers wrapped in your arms. You've been hiding them in hollowed out pianos left in the dark. Got the music in your baby, tell me why. Got the music in your baby, tell me why. You've been locked in there forever and you just can't say goodbye.
Yes, to be able to build a car as amazing as Freya, you need a team. And for Chalmers Formula students, this means a whole new team each year. We build a whole new car every year, which is 95% built in-house. It's fully electric and self-driving. We have over 70 students in our team, and we have nationalities from all around the world and all around Chalmers. In this year's team, we have 11 different nationalities from Canada, South Korea, and all over the world. And then we also have from all around Chalmers, and most of the students study mechanical engineering, which is not a surprise when you're building a car. And this year's team, I'm very happy to present the team of 2025. Here are my teammates. In this year's team, we are 8 different subgroups that work with different things of the car, and you're going to hear from all of the subgroups in a moment. But we have 3 different roles in the team. We have our project managers that were a part of the team last year, and they help us with their expertise. And there's one manager for each subgroup that help the subgroup out. And then we have our project engineers, which is the majority of the team, and they study their masters at Chalmers. And then we have our junior engineers, which are studying their bachelors. And a year for Chalmers Formula students starts in September, and that's when the new team is recruited. Then, when we have settled in the new team, the design phase starts, and we start designing the upcoming year's car. And then we go in, the design phase is during the whole fall. And then during the spring, we start with the manufacturing. And then when the car is ready and has 4 wheels on it, we reveal it. And we start testing during the whole summer until it's time for competition. And this year, we're going to 2 different competitions. We're going to FS Germany and FS Czech Republic. And now you're wondering, and why you're all here, is to see what have we designed and who are we building right now. And the car of 2025 is Svea.
Extremely impressive run from the team from Chalmers. Team members are so happy.
Talking about speed, that time is again faster.
And before I hand over to the rest of the subgroups that are going to tell you about what they have been designing, I want to present my subgroup because we don't do any designing of the car. So this is the business and marketing team that I have been working with, and we handle external communication. So we handle communication with sponsors, our social media, and then we're also responsible for the business plan during competition. So I want to give a big welcome to Vincent from the Aerodynamics subgroups. We handle external communication. So we handle communication with sponsors, our social media, and then we're also responsible for the business plan during competition. So I want to give a big welcome to Vincent from the Aerodynamics.
Thank you, Jessica, and once again, welcome everyone. My name is Vincent, and I'm a part of the Aerodynamics subgroup, along with these fine gentlemen right here. So let me start by explaining what it is that we do. We design parts for the car that help it move faster and handle better by utilizing the airflow around it. So you might be familiar with the term downforce. As the name suggests, it's a force acting down on the car, pushing it to the ground. And this improves the stability and the grip of the car, allowing it to take corners at higher speeds. And this allows us to cut down lap times in competition, and it's important for placing yourself among the top teams in Formula Student. So how do we do this? Well, we start by designing our parts using CAD software, and this could mean something like changing the geometry or the angle of a part, or designing a completely new one. We then simulate the car using this new design, using CFD software, and you can see this as sort of a digital wind tunnel. And this simulation will tell us how much downforce and how much drag our car produces with this design. Finally, we analyze the results from the simulation by looking at the data and the images, and hopefully from this we can understand why our design worked or why it didn't. And then we go back to the drawing board and try to further improve our design. So let's take a look at the aerodynamic package for Svea. It looks like this. And you can say that we have 4 main aerodynamic devices. So starting from the front, we have the front wing, which generates the majority of the front end downforce, but also affects a lot of the air to the rest of the car. Next, we have the side wings, which manage the airflow on the sides of the car, but also deflects a lot of the air to the underbody and to the rear wing. On the back of the car, we have the diffuser, which helps expand the air from the underbody, which increases the so-called ground effect, which sucks the car to the ground. And finally, we have the rear wing, which by its sheer size produces most of the rear end downforce. So let's take a look at the key changes and improvements regarding aerodynamics this year. So first off, we have a completely new chassis design, and we have made sure that parts of the design are as beneficial for aerodynamics as possible. So for example, the angle of the rear slant has been optimized for optimal diffusion of the air. We also have a new diffuser design, which follows the shape of the new chassis. Our side wings have a completely new side wing profile, which by itself has increased downforce significantly. And for this year, we also have the radiators and fans placed on the side wings. And we have simulated the positioning of the radiators and fans to ensure that we use the airflow from the fans to optimize the performance as good as possible. So these changes sound really nice, but what does it mean in terms of numbers? Well, we can probably say that our work has resulted in a 9% increase in downforce with a final CLA of 5.5. And while doing this, we have also been able to achieve a 5.6% decrease in drag. with a final CEA of 1.7. And with that, I will leave the stage for Filippo and Hannes to present chassis and ergonomics. Thank you. And while doing this, we have also been able to achieve a 5.6% decrease in drag with a final CEA of 1.7. And with that, I will leave the stage for Filippo and Hannes.
Thank you very much, Vincent. And as anticipated, I will introduce the chassis and ergonomics subgroup. However, Hannes will give you a few more insights on the ergonomics part. Okay, so what is a chassis? Basically, each car needs a very solid and light foundation where every component can be attached to. This is the chassis we designed for CFS25 Svea. As you might understand, safety is our priority when it comes to driving because we are reaching high speeds in very unpredictable tracks at times. So we have many structures that have to be rules compliant to provide a safe platform where a driver can be performing and be safe at the same time. As you can see, many of the structures, as for the impact attenuator at the front, have the role of absorbing energy in case of an impact. So we are absolutely focused on that. Okay, but let's dive in on the composite material part. So our chassis is made of carbon fibers and an aluminum core. An aluminum core is in between a sandwich of fibers that take most of the load, transferring it from the back of the car to the front and from the left side to the right side. These fibers are cured in an autoclave, which is a pressurized oven that will allow the fibers to become very stiff, but at the same time maintain their lightweight. What changed for 25? Basically, the shape was revolutionized by a very narrow shape at the back, thanks to power electronics, which went through major changes, but Ole will go through it later. And this also allowed us to change the layup of the carbon fibers that go through the shape of the car. Basically, a weight reduction of 16%, which is a great improvement from last year. I will let Hannes introduce you to the ergonomics part. And this also allowed us to change the layup of the carbon fibers that go through the shape of the car. Basically, a weight reduction of 16%.
Yes, so my name is Hannes, and I'm the main person in charge of ergonomics this year. As Filippo mentioned, safety is a huge factor whenever we're designing a car for our students. Not only is safety important, but so is driver comfortability. And that's where ergonomics come in. And this year, we managed to find a way to make a seat mold, as you can see here to the left, that is very precisely molded after our drivers, which could then be put into CAD and used as a reference to design a proper seat fitting for this year's drivers. As you might know, we have 4 different drivers at the same time that all need to be comfortable while driving the car. And therefore, we're using a half-seat solution, as you can tell. And so the seat itself will hold the pelvis in place, and then the shoulder padding makes up for the stability in the upper region of the body. And with this, we hope to allow the drivers to feel comfortable while driving, while also staying safe, of course. And with that, I will hand it over to Eloi, who will go through suspension. And with this, we hope to allow the drivers to feel comfortable while driving, while also staying safe.
Hello, my name is Eloi. I'm part of a suspension subgroup for CFS25, and this is our subsystem for this year. So the main goal of the suspension is to dictate the behavior of the car through different dynamic events. So that's cornering, braking, acceleration. But it is also to provide proper ride comfort and drivability for all of our drivers. This is done by transferring the forces from the tires to the chassis through each and every part. So the main sub-assemblies that compose this huge assembly are the front and rear wheel packages and the front and rear actuation and linkages. We will go through them one by one to show the new improvements for CFS25. So for the front wheel package, as you can see, there is a lot of organic looking parts. This is due to a combination of topology optimization and metal 3D printing. Topology optimization is a method, a very powerful method to optimize the design of mechanical components. In our case, we have used it to rearrange the material in the parts to maximize the stiffness while achieving a certain mass objective. And this has allowed us to triple the stiffness of our wheel package while having a 40% lighter parts. For the rear wheel package, as you can see, it is very similar to the front, but the size and the shapes of some of the parts is different. This reflects how every part is optimized for its own individual load case and to maximize the performance. Interesting to note also for this year, the cooling for our in-wheel motors has been integrated within the upright for better use of material. But Ole will go deeper into that. For the rear actuation and linkages, due to the new monocoque design, we have moved the dampers and spring to a longitudinal placement within the car. This improves the agility of the car by moving more mass towards the center of gravity and reducing the yaw inertia. Also for this year, we have a carbon fiber adjustable anti-roll bar to fine-tune the balance of the car to the likings of every driver that we have. As Hannes mentioned, we have 4 drivers, so they all have their own preferences when it comes to driving the car. For the front actuation and linkages, we have kept the same concept as last year with the dampers and spring in line with the push rod. However, new for this year, we have figured out a way to have 2 different front suspension setups, one for driverless and one for manual driving. And this is a big improvement because the dynamics of the car change quite a lot, whether there's a driver or not in the car. So this allows us to have optimal driving characteristics for every condition with minimal compromises. Interesting to note also for this year, our damper mounts, both front and rear, have been topology optimized and will be 3D printed in high strength steel. I will now leave the floor to Ole to present the mechanical powertrain.
Okay, so my name is Ole and I will represent the mechanical powertrain subgroup. So what is the mechanical powertrain of the car? It is essentially everything that propels the car forward. It's from the energy source, the battery, to the wheels and the gearboxes. So we have a lot of things that we have done this year, so I will just give you some highlights, what we are working with. For the energy storage itself, we call it the T-sack. It's the battery and the relay box combined. For this year, we have kept the same segment design as we have used previously, as it has been proven to be a good design. But we have been working a lot about the outside of the T-sack. We have managed to reduce the weight of the mounting solution by 60%. With some new components that we'll talk about very soon, we also have a new case of thermal management of the T-sack. So we have been working with a new air cooling system for the T-sack. The DC from the battery are then converted into 3-phase AC into the motors using an inverter. For this year, we have a completely new inverter. As we have previously heard, we have made it possible to reduce the width of the rear of the mono by implementing this new inverter. It has also been 50% lighter with this new inverter. It has also some new nice features like 4 times higher switch frequency for faster torque response, built-in speed controller, and some better cable management. And then we've also manufactured and designed new in-house motors. These new motors have a 25% higher peak torque, but still 20% lighter. This is due to a smaller size and a lower electrical weight, but also some nice new features like a shaft in titanium. And with the new motor comes the possibility for new cooling for the motor. So this year we integrated the cooling into the upright, as Alain has already mentioned.
This gave us some more design freedom, so we have managed to, for the same cooling capabilities, reduce the pressure drop by 52%. And with that, I will hand over to Lina and electronics. Into the upright, as Ella has already mentioned. This gave us some more design freedom, so we have managed to, for the same cooling capabilities, reduce the pressure drop by 52%.
Hello, my name is Lina and I am part of the electronics subgroup, and here you can see my teammates. An overview of our system, what we do is we handle communication between different parts of the car, and we handle sensor inputs and some safety systems. And the goal for this year is to reduce the complexity and weight of our system. So we will begin by doing a little comparison between last year and this year. Last year, a lot of the components were scattered around the car, mostly the autonomous parts, which are highlighted in purple. But this year, we have a more compact solution for packaging, so we don't need that many cables, which enables us to minimize the weight of the harness. We have also designed new nodes for this year. We were able to move a lot of the components from the front to the rear, which allowed for a smaller front node. And for the dash, we completely removed the dash node and only kept the dash itself. And this also allowed for a thinner dash in general, which gives us more ergonomic solution for the drivers. And while moving a lot of components from the front to the rear still managed to keep around the same size as it was last year. And thereby we were able to reduce the overall size. We have also implemented a new followers for our battery management system, which has given us higher accuracy in voltage readings, but also cell temperatures. And with the new followers, we've also needed to develop new drivers to implement the communication. And with this, I will hand over to Hampus from Control. And with the new followers, we've also needed to develop new drivers to implement the communication. And with this, I will hand over to Hampus from Control.
Hello everyone, my name is Hampus and I'm part of the Control subgroup. And up until this point, you've been presented with all the high-performing hardware of the car. But how do we make sure that we utilize it to its fullest potential? For this, we need a control system. And our control system works in 3 stages. First, the sensor processing stage, where we take signals from all over the car and input them to filters to increase their quality and reduce noise levels. Then we have the estimation stage, where we take the signals from the previous stage and input to estimation models. This we do in order to get a good idea of what the driver wants and how far the car is from its limits. This could be things such as how fast the driver wants the car to turn, or how much energy we still have in the battery. The last and most important stage is the torque vectoring stage. Because you see, a regular car usually splits the power between each driving wheel with the help of mechanical differential. But since our car has 4 independent electric motors, we can control exactly how much power is sent to each wheel 100 times every second. This allows us to optimize power delivery based on available grip, aiming to improve traction and performance. It, for instance, assists the driver in taking corners by essentially applying a torque bias, as shown in the picture. A key goal in the control system this year has been efficiency, which is an advancement propelled by the new pedal box design, which completely separates regenerative and mechanical braking. Regenerative braking is crucial for drive cycle efficiency, as it captures energy through the motors instead of wasting it as heat in the mechanical brakes. In previous years, regenerative braking could only operate alongside mechanical braking. But this year, we will instead, the first 90% of the brake travel will instead be purely regenerative. By having this more by having more control over this and creating a seamless transition between mechanical and regenerative braking, we can allow for a more drive cycle efficiency. Alongside this, we have also implemented an algorithm ensuring maximum regeneration and discharge of the battery while still respecting all the hardware limits of the battery itself. And by this, I welcome Nicholas from the autonomous system. And discharge of the battery while still respecting all the hardware limits of the battery itself. And by this, I welcome Nicholas from the autonomous system.
Hello everyone, my name is Nicholas and I'm part of the autonomous subgroup, and this is the rest of my team. We are responsible for making the car drive autonomously, meaning without a driver. But you might be wondering, how is it possible? How can you get the car to drive without a driver? So I will today go through the steps we take to be able to drive without a driver. So first and foremost, we have the lidar, which is the eye of the car. This sends out light and works kind of like a radar, but with light instead, and retrieves this and creates a 3D image of the world around it in the form of a point cloud. This year we have changed LiDAR to a new one with greater perception range, as you can see on the right, compared to the old one on the left. This will make us able to detect cones that are further away, so we can see further than previously. So now we have the first step, which is seeing the cones. So the second step is to take these cones and trying to build a map. And this is done using the SLAM algorithm, which stands for Simultaneous Localization Mapping. This is kind of a chicken and an egg problem, because in order to create a map around you, you need to know where you are. But in order to know where you are, you need to have a map. So we fix this with SLAM. So when we have the cones and now a map, we need to do a path. And that's when the path planning node comes in. What we do in the first lap currently is that we follow the gray line, which is center line between the cones. But then when we close the track, we have an optimization problem and try to minimize curvature to find a more optimal racing line. The new change we're looking into this year is trying with a sliding window approach to do this even the first lap when we don't know the whole track. So now we have the cones, we have a map, and we have a path. This path is then sent to the autonomous control system, to a longitudinal and latitudinal controllers. These are used to calculate the torques we can produce in the motors and also the steering angle. Something that we are looking into this year is doing an adaptive velocity planner, meaning the car will feel how it feels every part of the track and try to go faster or slower depending on some errors. We have also changed the driverless PC this year to a much smaller one, the NVIDIA Jetson Nano Origin. And this is also more like in the robotics industry and used in all of robotics. So now we have everything we need, and if you follow these steps and tune it just right, you might end up with something that looks like this.
Do we see solid blue light? Yes, we do. Extremely impressive run from the team from Chalmers.
Now Jessica will go through some of the team goals for this year.
Yes, when you're working a very big team with different stuff, it's important to have some common goals. And these are some of our goals this year. And the first goal is that we want Svea to weigh below than 205 kilos. We want Svea to be ready for testing by the 15th of June. And then we want to be able to test 250 kilometers manual testing and 75 kilometers of autonomous testing. And then not a very official goal, but a very important goal when you're working a very big team is having fun and working together. And before I tell my teammates to come up here and give them a big applause. I want to thank all our sponsors that make this possible. So our VIP sponsors, Aros, Essek, Volvo Cars, our gold sponsors, AFRY, Diabetics, Höganäs, Condesign, SKF, Hexagon, Wireless Car, and EMC Services. Our silver sponsors, CEPAC, Ansys, Wiretronics, SSAB, Beta, EDR Midesso, and our bronze sponsors. Thank you very much. And after the team comes up here, there's going to be some fika outside, and we're very happy to mingle with all of you and tell you a bit more about the different subgroups and what we have been working on. So welcome the team of 2025 on stage. And after the team comes up here, there's going to be some fika outside, and we're very happy to mingle with all of you and tell you a bit more about the different subgroups and what we have been working on. So welcome the team of 2025 on stage.